My name's Steve Glass. I'm a software developer. I'm sometimes a researcher and very rarely an educator. And I've got a specialist interest in network and software security. So today's talk is actually on the subject, as I said, of iOS security, specifically looking at Wi-Fi as an attack vector and diving into the WNIC itself as the object of attack, subject of the attack. So, been quite a few iOS things in the news over the last 12 months. I don't know if you've noticed. There was a report just came out of Citizen Lab in Toronto not so long ago, which listed a whole heap of cases where people had had their iPhones compromised by malware. Probably the highest profile one you've heard of is that of the murder of Jamal Khashoggi just a few months ago in Turkey by the Saudi authorities. And it was reported that his phone had been compromised by a particular piece of software. And in that report that Citizen Lab put out, they actually listed a whole heap of other incidents around the world where the work of one piece of software or malware that you probably are familiar with came up again and again and again. And that was the PEGASUS malware, which is sold by the Israeli company NSO Group. I'll say Israeli, they're actually an American-owned outfit. But they basically have a track record of supplying some of the most vicious regimes around the world and some very dodgy customers. So we've got examples I've listed up here of a Saudi citizen in Canada who found his phone bugged. We've had Ethiopian expatriates in London having their phones bugged. We've had activists against corruption, anti-corruption activists in Mexico who've been fighting to find out what's happened to some of the missing relatives because they believe they've been victims of cartels. They found themselves victims of the same malware. It was even used against Ahmed Mansour, which is why we all know about Pegasus. He was the guy that provided the very first hot link to the Citizen Lab people who got the tech analysts in on it. And he basically received a text telling him, secret report detailing torture in UAE prisons, because that's where he was living in the United Arab Emirates. Click this link. Now, we'd been fooled several times before by Gamma Group software, by Hacking Team software. They'd gone after him year after year because he's got this kind of record. And he'd spoken to Citizen Lab and they'd set up a sting operation where they clicked the link for him. They downloaded the first stage of the malware loader. Then they got the second stage to come down. And then from there, that's where we all found out about Pegasus. So how do things like that work? Well, on iPhone, there is a slightly different approach to if you were going to pop a normal shell on a normal box. Basically, we've got to get remote code execution to start with, and the usual target is going to be Safari because the attack surface on an iOS machine is almost non-existent. If you look at the things that's listening for network inbound connections, there's very, very little to go after. But then you've got Safari, millions of lines of code designed to run remotely provided, unsigned code. That's awesome. That's a great place to go in. So Safari is targeted for that reason, but it brings in a whole heap of countermeasures. It's got ASLR, it's got write XOR execute, it's got stack canaries, it's got a restrictive entitlements model in terms of what that process can do, even when it's compromised. But Pegasus managed to use a use after free exploit to gain native code execution. That was good. That's their first step. That doesn't get you very far, though. I said there's a restrictive sandbox in place. It's enforced by a daemon called AmphiD, and that's the Apple Mobile File Integrity daemon. And its job, basically, is to run almost every process in the system runs as the mobile user 500, with very, very limited rights on what it can do. Any additional rights are granted by a system of mandatory access controls called entitlements. And so if you don't have the right entitlement, you just can't get anywhere. You're not going anywhere. You've got native code execution, big yip. It's not much better than Java. You've got to go beyond. Now, the step that people often do is a sandbox escape. Find another process on a system, more privileged than you, compromise that, execute with its privileges. But still, you're going to find that even root can't do that much on an iPhone. It's really well protected. It's subject to all the same controls. Those mandatory access controls are totally different to what we're normally used to in the Unix world. In Unix, we have discretionary access controls, where someone can sort of say, I'm super user, I can reduce the privileges. That doesn't work. So what you're forced to do as a malware writer is go after the kernel. Get a kernel level compromise, because that's really the next step up. And Apple is continuously raising the bar here, and they're moving things out, so it's making it much, much more difficult. The kernel itself uses all the same suite of protections. It's got a kernel ASLR mechanism, write X or execute, etc. And it's backed up by hardware integrity protections. You do anything even slightly dodgy in the kernel, and bang, the machine reboots. And that's in hardware. And from the analyses I've read, the necessary conditions on that are unlikely to be violated very trivially. And so it's a very, very strong guarantee. But assuming you've got there, and they actually use two separate approaches here. They had to get a 0 day to give them an info leak on where the kernel had slid to, and then they used another exploit pretty much in the same piece of code to give them code execution in the context of kernel. At that point, you can start awarding yourself the kind of privileges you want. You can start disabling the restrictions that AMFID puts in place, and you could get far more control over the device. But even then, the job's not completely over, because it turns out that most of the data on an iPhone, when at rest, is encrypted. So they have to use the level of access they've just got to insert shims, basically to insert themselves or interpose themselves between the application, the libraries, because most of the application data that you want is encrypted on disk. And right at the end, well, you've got the usual jobs of snooping and persistence and stuff like that. Persistence is really hard because every time you reboot the machine, you in effect have to re-jailbreak it, you have to re-exploit it from scratch. They did that by linking one of the startup items to be JSC, the JavaScript core, and executing a JavaScript program to repeat the same initial infection mechanism. But it was difficult. And what people have tried to do instead is find new attack surfaces. Because if you've got to phish somebody and get them to click a link, that's an point of exposure. You can have a time-limited link, it can be good for one time only, but it's a very limited way into the machine. And it's not very trustworthy. And recently we've heard about the UAE's own malware, which is targeting iMessage. And this Karma malware, as it's known, claims to be able to get you remote access without you doing anything. So it reduces the risk of detection very significantly. So you can go after games, we can go after other things, but maybe there's a different way of doing things. And the people at Keen Lab, they came up with a really interesting point-to-own entry last year, where they went after the, they went after the captive portal software. So I came up here on the train today with Queensland Rail. You connect to Queensland Wi-Fi, and up pops a page saying, do you accept our terms of agreements? Click yes. And that's because every time the interface comes up, the websheet portal gets a chance to say, can I contact captive.apple.com and receive the web page I think I can? If it gets anything else, it displays it to the user. And it uses the same WebKit framework and the same attack surface that you'd have in the Safari, but you don't get the user having to click on anything. But to get it to work, you've got to descend the stack a bit because you've got to run an evil twin sort of Wi-Fi attack where you have a fake access point that's putting up a fake page that's saying, I'm a captive portal, you can connect to me, or Google, or whatever it is you think you were going to, and then runs the exploit code. But still, it's a little bit clunky, and there's been a drive to go down that stack rather than going across the applications and seeing what else we can do. And if you go down the stack, you can actually address traffic at the different layers. You can see we can send different things to the IP layer. It's not really great hunting ground, but there's stuff in there that you might be able to exploit. Or you can go after the link layer. And at the link layer, we've got two separate ones that we can go after that are obvious, that have got like some kind of a distance between you and the compromised machine. And that's Wi-Fi and 4G. So today I'm talking about Wi-Fi. I'm talking about actually attacking the WNIC itself. So why not 4G? Well, 4G is actually quite difficult to attack. A Wi-Fi is actually a little bit easier to experiment with, it's easier to play with, and gives you most of the same advantages without the problems of ACMA knocking on your door and saying, why are you broadcasting in restricted spectrum? And this does happen. It happened to my employers many years ago when we were in research. They had some 900 megahertz cards with Wi-Fi that were accidentally straying into the GSM band. And it didn't take very long for ACMA to come knocking and saying, you can't do that. And we got an edict from the top management saying, not going to happen. Not good. I run a 4G and 2G base station at home for experiments. That's using OpenBTS and Cirrus LTE. They're great things to play with, but they are not just complex, which is great from an exploitation viewpoint. We love to see complex things, but they're actually a little bit complex even to get just working to start with. And so Wi-Fi's got a much nicer feel to it, to be honest, and it is really easy to go after, because one of the things that we're talking, well, I'll talk about the protections, but there are far fewer protections going at this lower layer of the stack than if you go in through the application space. Every talk, when we talk about Wi-Fi, makes this fundamental distinction. And there's a big spectrum of possible implementations that Wi-Fi chips can have. So what we've got here is, I'm talking about soft Mac versus full Mac, and they're just two kind of points in a spectrum that goes from, at one hand, a completely hardware solution in which almost all the work is done in hardware, of framing and amplification and all the processing that goes on for Wi-Fi. But it'd be very inflexible and really wouldn't be suited to the real world. Or you could go to the other extreme and you could have a completely software-defined radio where the only hardware jobs were signal amplification at the antenna. Everything else could be done in software. The trouble with that is it introduces latencies, and things like Wi-Fi have got some very precise timing restrictions. You've got to respond within a few microseconds with an acknowledgement. You've got to respond with a few microseconds to certain requests. It's just not going to work. So what we ended up with is two approaches where the first one, we implement the full Mac approach, is the hardware does take on most of the jobs. In its internal design, both these approaches use something approaching a software radio thing. They don't expose the samples up to the higher layers. What they expose is frames, which is what we want to see. But in the case of the full Mac design, you have a processor that's not just implementing all those timing critical behaviors that I mentioned up here, things like CSMA, RTS, CTS, or acknowledgements, all of that stuff, but you will also implement the higher level behaviors that will, like probing, key authentication, exchange agreement, all that kind of thing will actually occur on the card as well, and not in the host CPU. What we've got mostly on desktop systems these days is the soft Mac approach, where the kernel, like the Linux kernel, has got its own 8211 stack built in, and it treats the card very much as a, here you are, you get to transmit this, but it's basically just a frame delivery service. It takes care of all those timing critical bits, but not the rest. The full Mac approach says, nah, we're going to offload all that hardware. And strangely, that's what the model has become for telephones, because you can actually do it on a lower power CPU all of its own. So rather than having the host kernel doing the stack processing, this stuff gets offloaded. So looking at the process that I've done basically has been to dive into this question, to research it and start doing a bit of reversing on the Wi-Fi card and trying to exploit it. And I've come up with a four-stage process. It's just interlocking. There's no kind of like, you do this, then you go on to do this. These things, you find a little bit out, you go back and you recycle around. And so try and research to understand the hardware, software. Reversing to actually understand how it works. Fuzzing to try and break it. And then exploit development to try and get on and see where we can go from there. So when we do research, I don't know if many people here are researchers, but probably the first thing in scientific research is study the related work. Look what other people have done already. And going back as far as about 2006, there was an attack against a soft Mac stack on the Macintosh by Elch and Maynor at Black Hat. And they proved that if there's a bug in the kernel stack for the 802.11, you get full kernel access immediately. Send a packet, bang, you've got access, and you can do anything you want. It was very controversial because they didn't release their exploit, they just hand-waved, and it wasn't for the actual chip used in the Macintosh at the time, it was used for an add-in card. It took about a year to get resolved. They did some really good work and they published it, but they did take an awful lot of rubbish in between time. Then there's the paper by Triolzi, or presentation by Triolzi, where he went after the network card itself, because it was common at this era that a typical Ethernet card would have its own processor. So maybe we can compromise the processor on the network card, use that position that running on that host to attack the host CPU directly from there. It's kind of a two-stage step. It's what I'm going to describe today. And this was the first paper. Then we've got a whole heap of others. Probably the most important that I want to highlight are the work of the NexMon people who did the same research and applied it to the WNIC, the Wi-Fi NICs. And they showed how you could actually reverse engineer the framework, the firmware, and modify it, upload new behaviors to the Wi-Fi card so that you could get monitor mode out of your iPhone, because that's something you can't do. But their work wasn't done on iPhone, that was all on Android. And then the paper by Beniamini was a set of 2 articles by Google's project. It was absolutely stunning piece of work, really good stuff. Beniamini showed a complete exploit chain of how you can exploit the WNIC and go all the way through to an iOS compromise. And right at the end, I'll talk about the final paper just at the end here, which was by Stutter and others, which talks about AWDL, so I'll come back to that. So that's the research, and all those things in the links, if you get the notes, they're all links to the presentation so you can download and go through. And hopefully my presentation today will give you a handle on how you can get more value out of studying those things and how you can actually use those results to get yourself execution, get yourself an exploit that at least runs on the WNIC. So the next part is to look at the publicly available data. What we've got there is the data sheets from Cypress, or Broadcom, the company that produces the chips. And all the Broadcom full Mac chips look very similar. They basically have a bus at the back end, they're very modular design, where these things called cores, and I've described them here as there's a PCIe core, and this acts as a bridge between the bus, the PCIe bus that the host is using, and the internal silicon backplane bus that all the other cores are connected to. And it allows you to basically present any one of those cores on the main PCI bus and switch between them. And those cores do things like, I've got an ARM Cortex CPU here, so that's what's actually running there. It's a 32-bit CPU just dedicated to doing network processing for Wi-Fi. That's all its only job is. It's got its own RAM and ROM. They can be read from the host device directly, or certainly the RAM can. Everybody has said that the ROM can't, and that's why it's shaded out that you can't access the ROM itself. We have a D11 core, now that stands for .11, 802.11, and that's for doing all the time-critical stuff on the CPU. That's not done by the Cortex running those high-level behaviors of key authentication exchange agreement, joining and disassociating from a particular logical network. This is the stuff to do with, I want to broadcast now, do I have to back off? Do I have to retransmit? Do I have to generate an acknowledgement? All those kind of really low-level time-critical stuff, they're done in the D11 core. And that's done using a programmable state machine architecture. There is a publicly available PSM assembler for that as well. So you can actually program that remotely if you can get access to the device and get access to the silicon backplane. The third, so I've said, it's just modular, and from the top end, they can be the same. They can change that PCI for other things. Earlier versions used a version of USB, that like hard-coded USB called HSIC. They've used SDIO, and all they have to do is change that one silicon backplane core, and they provide a new interface. So it provides a great deal of consistency all the way, and you'll see also on silicon backplane, the Bluetooth capabilities are also integrated onto most of these chips, and it'll appear as a core on the backplane. You also have some source code, always useful when reversing. Apple make much of the source code of X and U available. Most of the I/O kit stuff is available, and device drivers are a great place to find bugs. They've done some academic studies over the years. There's been some very famous papers. They find that the rate of bugs in core kernel code is about 7 times lower than the device drivers. So the I/O subsystem is a very flaky part of your average operating system. When you get Windows blue screens of death, it's usually down to some flaky device driver, not something in the core itself. The other thing that you're going to see is MDNS responder. Now that's Apple's mobile DNS implementation, but they do make the source code of some parts of that available, and that can be quite useful. We've got the Linux device driver for the soft Mac devices. Since they're programming and dealing with the same hardware that the full Mac device does, it's logical to assume that we've got that stuff to go. We've got the operating system that runs the full Mac chip. That Cortex runs a version of ThreadX. It's got its own monolithic operating system. It's all one big binary image, but it actually runs a version of ARM ThreadX. And then we've got some leaks that occurred of the source code from Broadcom. That's awesome. Got that from one of the earlier presentations. Martinstein, he pointed out, I went looking. The guys Milan Stutter's paper provides a link to them. And then about 18 months ago, I received a takedown notice because I'd simply forked it on GitHub. And that's what they've done. They've basically gone after both of these repositories. The VMG 1312B, I should have explained that black box up there. It's the source code for that box has become available in the VMG 1312B repository. And then the KHSIM is probably even better again, but you're not going to be able to get those legitimately just by Googling. You're going to have to join weird Russian or Chinese forums, I'm afraid. So proceeding on to actually the real meat and drink of what I meant to be, and I'm already 20 minutes in, it's reverse engineering. How can we reverse engineer the WNIC? Because we're not going to get an exploit unless we understand what's going on. And so we need to dive in and find out what's going on. You're going to need, for something like this, a reasonable setup, something where you've got a jailbroken phone to experiment with, some kind of controlled environment, computer to actually do the reversing on, and some disassembly software, disassembler. Now I use, and I'm in the slides here, I'm actually using mostly Hopper. I don't know if anybody uses Hopper. I think Hopper is awesome. I'm not a fan of IDA. I think it's a piece of rubbish. It's very complex, but it's rubbish. And of course, we've got Ghidra that's come out in the last few weeks. And I'd want to take a show of hands. How many people have downloaded Ghidra? How many like it? Okay. Yeah, it's quite good. It's a really useful tool to be going on with. In some ways, it's changed how I look at disassembly, because you're able to go a little bit further up the stack and start looking at things at a semantically higher level than just assembling. I'm good at assembler. I understand what I'm doing. I enjoy playing around at that level. But Ghidra allows you to go that little bit closer to C or something like that, and it's much more useful. So, the firmware. Now, I've said that the back end, the silicon backplane, has got this CPU, the WNIC CPU, the ARM Cortex. It's got RAM and ROM. Now, the ROM contains most of the behavior of the Wi-Fi stack. All the high-level behaviors are up there. And then there is some RAM, which provides like runtime scratchpad memory, places where all the message frames are going to get stored while they're being queued for transmission or queued from reception. And it also includes some patches. It includes changes to the ROM and firmware, because when I said about the spectrum of possible designs, if you do everything in hardware, it's really inflexible. If you do everything in software, it's really flexible. But the full Mac is kind of more towards the hardware end of that spectrum. But they still want the benefits of doing it in software. So what they do is they allow for patches to be shipped via RAM to the ROM program. And so it gives us a chance to dive in and have a see what's going on there. So I'm showing an example here is how the RAM actually gets initialized is that there's a process that runs on your iPhone called the Wi-Fi firmware loader daemon. It speaks to the kernel API, ultimately contacts the device driver, and because it's a full Mac device, the device driver is very thin and basically forwards almost all the calls made to it directly onto the device to satisfy. If you're a Macintosh, it would do much more of those inside the Mac kernel itself. But in the iOS kernel, it's forwarded on across to this device. So we want to recover as much as we can from the code from there in order to give us something that we can play with. And that leads me to this series of steps. Basically, the initial steps I'm suggesting is that you want to recover the firmware. Well, you're going to get the RAM, because that's something we can access. So we're going to find the RAM image. We're then going to reverse it sufficient, at least, to allow us to patch it so that we can insert a patch that will then let us get everything out of the ROM. And once we've got the ROM and the RAM images, we can glue them back together, and now we've got a piece of software that we can analyze properly inside our disassembler. So let's have a look at what steps involved. Where is the RAM image? How can I be sure I've got the right thing? Well, where is it? Can get in two ways, and this is a general approach that I've adopted in other cases as well. If you've got like an embedded device of any kind that's getting updates, probably the easiest way to get hold of some of the firmware on there is to look at one of the software updates, and that's what I've done here. Whenever Apple ship an update as across the internet to your device, it comes down off one of Apple's servers as a great big package. With a .ipsw extension. That's just another name for a .zip archive. You unzip the archive, you get a couple of disk images. You look inside the biggest disk image, you see a mirror of the file system that will be uploaded to your phone. You can't change it because it's digitally signed. Apple, if you try and modify that image and feed it to your phone, it'll go, it's not signed, or the signature doesn't compute for the file that you're giving me, not going to play. But if you just want to poke inside and get the software out, that's one way. The other way is to go in a jailbroken phone. You can actually, if you've got a jailbreak, you can get it that way, pull it straight off the file system. So if you dive down here, you can see I've gone in, and we've got user, share, firmware, Wi-Fi, and then we've got a couple of different options. And that's probably the first problem you've got is what do I have to pull apart to find out where I'm going? So it turns out that this one, the 43342 series is just a part number from Broadcom. And underneath it, you'll see that there are not just several directories at that level, but that one has got several different files underneath it. They vary in size. Probably the biggest one is the obvious one, is cabernet.trx there. That could be a good place to look. But how do we know which one to go after? Well, if you actually have got shell access, you can ask the Wi-Fi firmware loaded daemon, what would you load? Because you can, if you run the option, the command line you see here, -f will tell you what paths it is loading. And if you run it, that's what you get. Very little. On my phone, it just hangs there forever, and you have to Control-C. Later versions of the firmware will actually give you a breakdown. It'll say, well, I've got several things here. This is from, the first one's from an old iPhone 5S. This is from my iPhone 7. And on my iPhone 7, it says, oh, my firmware is in elsa.trx. I've got some NVRAM file, and that's in a .txt file. I've got a CLMB, which gives me regulatory restrictions on where the Wi-Fi goes. So you've got all the files. We know what they are. Now we know what the extensions are. The interesting one is the firmware is contained in the TRX file. Going back to the earlier problem where I asked the firmware daemon and it won't tell me what's going on, we can look in the IO registry. That's a database that's built at runtime, hierarchical database telling you, well, it's a three-dimensional hierarchical database, it's really weird, but it tells you what the firmware is doing on the device at any one time. It'll tell you what's loaded because you can grep for the firmware version. And if you pick that out, it comes up with a firmware ID. And so I grep for that firmware ID inside the files, and lo and behold, in this case, it is Cabernet that matches. I thought it was Chardonnay, but I was wrong. Cabernet matches. So the cabernet.trx is the file that we want to pull apart for that one. Elsa.trx for the other one. Apple have got all these different names. Some of them come from frozen, some of them come from wines. It's really quite strange. But once you've got it, you're ready to reverse it. Okay, so what we need to, probably the next step is find out what file format's in use, where does it get loaded in WNIC memory, and basically how we make sense of the image. And that's basically where I started off. So we'll have a look. Basically throw the file at binwalk. I mean, I'm sure most people have heard of binwalk. It's a really good tool. It'll match signatures, it'll do things. And the first thing that comes back and says, oh, TRX firmware header. So perhaps it was a clue. TRX is a commonly used firmware packaging tool. And it's telling us it's got some really interesting things going on here. Particularly, I like the fact that it says, oh, we've got a kernel offset, a root file system offset, we've got a bootloader offset. It sounds like Linux. This could be cool. I wonder. It's not Linux. What's happening is binwalk's trying to be a bit too helpful for you. It's not actually a Linux kernel at all. But the TRX file format is documented. It's a great thing. You go to the OpenWRT website, if you have a Google, it comes back, and you see something that looks like this little packet diagram at the side. So what we have is a magic number, HDR0. We have the length of the file, of all the bytes in the file following that, the CRC of all the bytes in the file following the CRC, and then we have 3 partition lengths. Now, in the OpenWRT thing, they say they're offsets, they're not their lengths. I know that it's a very subtle difference, but it allows you then to look at what's going on. And in the Apple firmwares, what you see, the header is always present. There is always a partition 0 or partition 1. Partition 0 will contain the firmware. Partition 0 is the big one. Partition 1 is 0 padded out to some arbitrary length, and they'll make all the different firmwares in one directory all have the same length, just so that they look nice when you LS them. I don't know what other reason they have for that. So the first step is to extract that green blob out. And so we do that, and we're going to throw it into XXD to see if we can make some sense of it. So this is me with XXD for cabernet.trx. What I've done, I've just exerted a bit from the start of the file, a bit from near the end of the file, and a bit right at the end of the file. So the first 2 are, if you like, the start and end of partition 0. And if I look at that, well, HDR0 can see that at the beginning. That's the kind of the metadata that we expect to see at the start of TRX file. It's all there. All pans out. The CRC computes correctly. Everything's fine. The next thing we see is what looks like some structured data. We're seeing these 0000 and then followed by an address. So because it's a little Endian architecture, those are kind of like low in memory. That's kind of a bit of a hint. But otherwise, it looks to me like some kind of exception vector. And I'd expect that on an ARM processor. I'd expect to see something down there that looks like an exception table or a jump table or something of that nature. At the end of the file, there's some textual metadata. That's interesting. So we've got the name of the file. There's that there's the firmware ID that we grabbed. There's a CRC in the file, but it's not the same CRC we saw earlier. But it kind of suggests that maybe there's a bit more going on. Well, I tried this, had a look at different things. My iPad Mini 2, because I've got some very old kit, lots of iPhone 5Ss, all of them great. I thought, great, we've got a solution now. I've got the firmware. And if you throw that file as is into a disassembler, it kind of works. But when I flicked to my newer phones, the iPhone 7, the iPhone 10, the iPad Pro, they don't work. Binwalk actually chokes on all of them, says, don't know what's going on in here. So we'll do the same thing, throw it into XXD, just quick hex dump. We don't see HDR at the top. We do see some structured data, some squinky sort of characters, but they're no longer like addresses, low in memory. In fact, they don't look like addresses an awful lot to me anyway, but I'm going to tell you the actual jump instructions. You throw that into the disassembler, it's going to see just a list of jump instructions. So it's an exception vector again. At the end of the file, we see the same kind of structured, same kind of metadata, textual metadata we saw before. And something I ignored in the last slide was there's a length field. And actually, that's the length of the preceding textual metadata. If you walk back 94 hexadecimal bytes, so 9 rows and then a couple of extras, you end up with exactly the length of that metadata string I've highlighted in pink. So maybe that's actually not part of the firmware image itself. In fact, if we take the file that we extracted from the earlier TRX file, it looks exactly like this. All Apple have done, in the newer formats, they've thrown away the external wrapper, they've stuck with the lower level one. But it's still a wrapper, it's still not the actual binary. All that stuff at the end isn't quite right yet. Because if you want to change anything, oh, sorry, there's your CRC, and again, the CRC doesn't compute. But there is, within the CRC, a clue about how we can understand what the data, how it's structured. And so, what I'm going to do, I'll skip ahead just a little. The next slide shows it quite well. What we have in the file is the firmware RAM image to start. At the very end, we have the length of the text metadata. We can step back. And then there's a fixed size block in between. And that block is, I think, 34 bytes. And it's always the same. The actual content of it changes from machine to machine and build to build. So, not really sure all of it, except the first part is a CRC, all the data prior to that CRC that precedes it. So I worked that out by literally computing and trying to find the textual CRC and find where it came from and just stepping through the file and say, oh yeah, there you go, and it's always the same offset. So that gives us something that we can now analyze. And when you want to try and analyze something, the first thing your disassembler is going to ask is, well, what kind of CPU have you got? Where do you want me to load this? What's the base address? And, oh, hang on, I don't know what the base address is. Haven't really, cool, I've just got this binary image. A couple of ways that we can work it out. You can guess, you can look at the previous history. There's been a lot of the published papers. If you look at Beniamini's paper, iPhone 7 is there. It's 160000, and that's where the RAM image goes every single time. Not the same on my ancient, my old-fashioned devices. All the ones with the Cortex M3 processor, it actually, they tend to load at 0, and that was my first guess, to be honest. I picked 0 out of my head, and then dropped them into the assembler, and do the symbols resolve? Do the branches resolve? The strings resolve? Does it work? It did. And then diving a little bit deeper, we started to see that there was a little bit more we could find out about the format. In that the TRX, the start of the data, I didn't go back when I showed you. I should have mentioned it, actually. Let's get it. In here. So, when I said about the structured data, you got this stuff there, and then down there's a string that stands out, DBPP. And immediately following that is something that does look a bit like an address, because it starts 1C, 2B, 10, and it's an address. It actually is an address. And I was thinking, well, that gives me an idea of where you might be able to load something. So you can pull things like that out. Turns out that DBPP string, if you Google it, you might come up with a Linux header file that tells you what's going on there. and that's a pointer to an important structure that exists in all these firmwares called HNDRTE debug. And it's got basically the fields listed from a little tool I wrote at the side there that I got just picking out things from actual iOS devices. So in this one, we can see a number of things, and it gives you the RAM base, the ROM base, the RAM size and the ROM size, a trap pointer, which is where the kernel will reset through. That address is 0 on this CPU. And it'll give you a pointer to the event log and the console. So there's a lot of information going on there. And it turns out that this DBPP occurs at a fixed offset, and it says here it's F8 bytes into the firmware image, always at address F8. And it turns out on the Apple devices, it actually can be at address 7.4 as well. And if it's at the lower address, it's followed by the actual load address, the pointer to the HNDRT debug struct that's listed over there, but it's also followed by the load address of the file. If it uses the earlier format, it always loads at address 0. So that's what we do. Throw it in there. This is the list I came up with, the devices I looked at. You can see that we've got different file formats. Some use the TRX wrapper. Some have gotten rid of the TRX wrapper and just use Apple's own no-tricks format. And then we have the different load addresses. They're either 0, and that's always in a processor with a Cortex-M3 processor, or it's got a different address when a Cortex-M4. So now we've got something we can look at inside the disassembler and start to reverse. We've also got that trap pointer, which gives us the starting point of the CPU, so we can start disassembly from there. That's really useful. So read address 0, find out what's doing, set the disassembler going. How do you make sense of just a random binary file? I've tried this on a couple of things. I did the OP25 project years ago. We didn't get very far with the Motorola radios, the police radios, when we pulled them apart. There was no strings in there of any kind. We didn't get there. Luckily, if you pull apart one of these binary images, you'll find quite a few strings in there. Again, we can name a couple hundred functions just from printfs that they're doing internally that go to an internal console that never is seen in the macOS world or the iOS world, but they do get logged on the device. And so you can look through and name functions. You can write a script to do it because they use the same functions, and it's always parameter X, and you can go through, pluck them out. So that's very useful. Other things is like constants. If you throw the binary at bin walk when you've got a complete binary, you're going to get SHA constants coming out. You're going to get the CRC polynomial table coming out. And it just gives you chunks of things. So you know, if something's referring to CRC table, that's a CRC function. Okay, you can move one step further along then. You can also look at neighboring code. When you've got some code that you understand, say I've got memcopy, then the compiler and the linker tend to put these things next to each other. Things from one translation unit tend to get linked in consecutive addresses. So what you'll tend to find is that you find memcopy, you'll find memset, you'll find memmove. They're all going to be in the same place together. And that's probably going to be near the rest of the standard library as well. The three things I've got along the bottom that helped me a lot to get used to this is the same data that's used by bindiff and stuff like that. These are metrics that your disassembler will make available to a script that you can pluck out. So give the parameter count and type. You can get the number of callers of a function, the number of callees. You can get the number of basic blocks, and you can get the number of edges between those basic blocks. That gives you a fingerprint unique to a function that's actually quite stable across different builds. So if you've, as I've done about 5 or 6 of these devices, I'll find that the strings name in a function exist in one binary, don't exist in another, but it still has the same overall signature. It still has the same number of parameters. It's still called by the same callers. It's still got the same callees. You can then port the name across quite trivially. Okay. So let's assume I've got a RAM image. I've started to disassemble it. I'm starting to make a little bit of sense of it. What's next? How do I patch it? So I suppose you've got to decide what's to patch. And it should really be something that's in the RAM sections. That's all the code I've got. We want to be able to trigger it deterministically, and we want to be able to trigger it from user space, and preferably pass data to and from. So that's really the starting point there. Now, how do we communicate with the patch kind of flows from what we're patching. How we patch, I'll go into that in a second. And what exactly should the patch do? So, flip it on. I'm going to use a mechanism that was first done by Blanco and Iceland in their presentation. That's basically patch a function in the device called the BMC device IOCTLS. Now, you're probably familiar, if you've done any kernel program on Unix, with an IOCTLS call where you basically get to speak direct to the device driver and provide some special device-specific magic. In the case of a full Mac card, the device driver basically turns around and passes most of those requests straight on to the actual device itself. And so the piece of code that I'm doing is emulating what the firmware loader does itself. When it has a piece of work to do, it calls the kernel API to the device driver, it talks to the Mac protocol, please do something for me, like load the image or whatever. In this case, I'm going to use the same mechanism where I pass an Apple 802.11 specific IOCTL, and that just bundles up a block of data in a special request structure, which when it's received by the card, it unpacks and calls this internal function, WLC IOCTL. Now, this is basically the central dispatching point for everything that goes on inside the WNIC. And if you have a look at it, this is a snapshot from what the actual chip does. It's got this great big branch table. As you can see, the load register call here is actually a branch. It's doing a switch. It's a 300-way switch inside the code. It's quite easy to spot. But the trouble is it's in ROM, and we don't have the ROM yet. But fortunately for us, Broadcom made it easy because they knew that they were going to be able to patch stuff. They wanted to be able to ship updates to their software. And so they use something called a patch mod vector, that all functions that are intended to be overridden by updates, that they can basically ship a RAM update and it will find it because it will look at a certain location at the start of memory and say, is there an update for WLC IOCTL? If it is, it calls it. When the result comes back, it says, did you handle it or do I handle it? If it handle it, fine, it then returns. But otherwise, it goes to its normal logic. And we can repurpose that so that we can intercept it and do what we want. But first, we've got to find it. And the good news is WLC IOCTL patch mod is almost always there. When you've got 300-way switches and you've got functionality that's changing and it's exposed to the user level, this function gets overridden. And we're lucky, or if you're lucky, the iPhone 7 actually names it in a little log message. Easy, job done, found. If you don't have that, the iPhone 10 doesn't actually even implement it. In the version of 11.3, I think it didn't implement it. I think they did it later, but didn't do it then. So you've got to go and have a bit of a look. And the way that I look is to say, well, WLC IOCTL patch mod, I happen to know because I've reverse engineered it several times now, takes 5 parameters. And 3 of those come from that user piece of code that I presented earlier. Didn't actually go, sorry, I'll pull it up. That little piece of code comes from my userland utility that emulates what Apple's code does. It populates a number of fields. They get unpacked and passed across. So we control some of the data. And I know it's 5 parameters. There are 3,000 functions in the RAM patch, typically that you're going to pull out. That's a lot of code to look through, especially because it all looks the same binary code until you've got some names behind it. But there are only 100 that have 5 parameters. It's immediately a smaller target. And you can write a little bit of scriptery and says, of those 5 parameter ones, are any referred to by the patch mod vector? Because that's where it would have to come from. And it turns out that you've got a handful, 13 of those are in the patch mod vector. So you can find that function then by a process of inspection. So this is what it looks like if you actually look at the patch mod vector, just as assembly without any names or anything else. It kind of doesn't really pop at you. But if you know what you're looking, it becomes a lot easier. If it isn't implemented, the job's more difficult because you only control 2 of the 5 parameters. But I'll show you how we can insert a patch. Well, we won't talk about that today. We've got time, I don't think. Right. Patching. How do we patch? What I've done is there's differences of approaches. The safest and the best approach, and the one that I use for programmatic approaches, is to have an external implementation of my patch that's going to read the ROM and an external invocation. So what I mean by that is I find a string in memory and I'm going to overwrite it. I find a nice long string, and this happens to be this one. Don't even think it's the longest, like 300 bytes long. If I null out the first couple of bytes, anybody doing a printf just gets nothing. That's fine, I don't care, I'm not really looking at that at the moment. I want the storage, I'm going to reclaim it and repurpose it. So I'm going to put some code into that storage, but I'm going to make the first couple of bytes nulls. And I'm going to have that code basically call the original code that would have been called anyway. And all I do is change the patch mod vector to point at it, and it's going in and saying, right, are you the IOCTL that Steve has hijacked? I'm going to take control of WLC dump. and I'm going to use it to implement my functionality. And if it's not my function, it's going to pass on straight to handle it over to the standard patch mod function. That's very easy. That's quite safe. The alternative is to actually do an internal invocation where basically you overwrite part of the existing binary. You find some functionality that you think, this WLC IOCTL patch mod function is doing something I don't care for it to do. I'll null it all out. Or I'll make it call some external code that I've written in a string somewhere else, but I'll duplicate this functionality. What I've done here is the most dangerous one, where basically these couple of basic blocks that are listed here, all dominated by the one at the top, and all of those handle one specific IOCTL call that I don't care about. So I'm going to steal it for myself, so I just knock all that data out, and I'm going to overwrite it with my code, just have it execute in place. Now that's dangerous because I'm changing the behavior of the thing that I'm modifying, but it works. I wouldn't recommend it, but you can do it from time to time. So now we've got how we can do it. We know what we're doing. We know we found the target. What should it do? Turns out that getting hold of the ROM is really, really, really easy. If you do a bit of reverse engineering, I pulled up memcopy. Memcopy is a great function because it takes one block from here, moves it over there. Doesn't work if the input parameter is null, unfortunately. So if you want to read data starting at 0, you might have to start at 4 bytes instead of 0, but you can get most of the data that way. And all this does, a couple of instructions, 3 of them are setting up the parameters, and then 2 to call. And I'm using 2 to call only because I want to be able to put my patch anywhere in memory. But since I'm writing assembly code, and since I'm going through the pain of patching it and doing all this stuff, the shenanigans of getting into memory to begin with, maybe there's a few other things we can do. We can build a debug platform. We can build some tools that's going to allow us to do a lot more later on. And so I've come up with these 5 functions, because I think that's all you ever need. That gives you everything you need to do. Read, write, exec, alloc, and free. And that is exposed with a user tool I'll show you in a second. And at that point, you should be able to bundle everything up, recompute the CRCs, because you know how they are, and put it back in the file system under user share Wi-Fi, appropriate file name, and Apple should just load it for you, but they won't. Because what they did in 11.3 was they introduced a HASHSTORE into the kernel. And that's got the hashes of all the firmwares it's going to load, nothing else. Basically, if you change 1 bit in any of the 4 files it needs, you're done. Game over. It'll refuse to load the firmware full stop. It's an equivalent to what happens with AP ticket with the baseband firmwares, with the 4G, when that's loaded onto the baseband processor. They've just said we want the same thing. They just used a slightly different mechanism. So how do we get past that? Well, I did actually have a really clever solution, but I'm not going to present it here because a much, much easier one came up. And it's very, very straightforward. It's actually documented in the Beniamini article. In that, if the kernel won't load the data for me, and I've got a jailbroken device, why don't I just do it myself? I've got kernel level access, I can do what I want. And it turns out that in the PCI Express standard, there's a concept where you can map part of the address range of the host system, that any reads or writes are then forwarded across this PCIe bus to the back-end processor, and they result in reads or writes to the memory of the WNIC itself, of the R4 processor or the M3 processors running there. And if you read the original articles by Beniamini, they're a bit unclear because they don't get the names quite right, but talks about what they call tightly coupled memory. And that's just basically that block of memory that you've mapped that's shared. You allow any reads or writes to that part of your address space to in effect be satisfied by the WNIC's memory itself. And if you do a bit of reverse engineering, you'll come up with 4 sets of write methods and 4 sets of read methods on an object called the Apple BCM WLAN chip memory. That's a big mouthful, but it's an object in memory in the kernel, part of IOKit that allows you to make calls and do the reads or writes. And if you look at how the implementation works here for a 32-bit version, it has an array of mappings which have the host address, the device address, and the length of the block. And it walks through and says, well, I happen to know that the bus index always is 5, because if you reverse engineer, you see the call, it's always the 5th element we use for this array. And it just does a little bit of pointer arithmetic to find the memory. We can do the same thing using a tool that was written by Brandon Hazard called memcontrol. Brandon Hazard should be famous because he's the guy who did the PAC bypass for pointer authentication recently for Google's Project Zero, or the first one. They've now got a second one that they're doing. memcontrol, as long as you've got a jailbroken kernel, will allow you to read and write arbitrary kernel memory. You've got to do it right. If you try and write memory that's outside of or it's inside the read-only region, it's going to reset. If you do a misaligned read or write, it's going to reset. There's all those kind of hardware protection things going on, but it's a really powerful tool. So what we do, we say, find class Apple BCM waveland chip memory. And if I do that, it'll come back with the address of the one and only object in memory that's got that. Because there's only got one PCI bus and one WNIC. It's only one of these instantiated. I can ask its size, and it'll come back and tell me it's 208 bytes. Those two pieces of information allow me to read the block, and now I get something that actually looks quite useful. Now, it probably doesn't to you right now because you've not done the reversing, but I can tell you that here we have our sets of mappings. So we've got 6 mappings there. I've told you that the fifth element is the one we wanted, and there's the address in memory of where the WNIC's RAM is mapped into the host memory. I can use that to rewrite anything in that memory I want. So I can step around the SHA protection mechanisms because I've got a jailbroken phone. It's still a worthwhile bypass because it stops this thing being used as a backdoor persistence mechanism, which is what I was planning on using it for. But no, can't do that. You can read there, and if you read under my highlighting, oops, let me go back again. I'm not driving this well today because I don't have my iPad. My iPad's not working. Right. If you look under that address 91000, you can see that there's a length field, A1000. You can also see that the address is mapped into the child process is 160000. So that's the address that it's on the WNIC. So we use that to read. And I'll read just the first 100 hex bytes. And we see exactly the same bytes that we saw in the file when we looked at the TRX file. We've even got the fa stuff. DBPP is in there. We now have, as well, the pointer, the 102B1C value for the HND RTE debug struct. So we can actually read that. We can now play. We can actually change things. Implementing my patching approach that I talked about earlier, this is where that string that I was looking at, basically, I found a string inside my the debugger. I knew what the offset was. I did a little bit of arithmetic to come up based on that base address with what it is, and now I've listed the first 120 hex bytes, and we can see you've got something here where there's a string. It starts stop check, but the second string is new line D3 underscore suspend blah, 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 blah. Okay. Reread it again, but this time I'm going to actually change it. So now I've done a write data command, and memcontrol is really good like this. It allows me to force a read, even if it thinks memory's unmapped. That's what the -Fs are everywhere in these commands. And I've nulled out the D3 underscore S. So if anybody prints that original string, they get a new line, end of.
You're one behind.
Oh, sorry. I am one behind. I'm not showing you the right thing. Right. So the first command up there is writing and nulling out the block of memory. Then we want to upload our patch into the remainder. Now, I deliberately padded out to the 4-byte boundary, because if you don't do 4-byte boundary, you're going to get a hardware reset. It's all going to go very wrong on you. And I've uploaded the patch, and this is what the binary of the patch looks like. It's 108 bytes. It does read, write, alloc, free, and exec. And exec serves dual use as well, because that's what we use for rebooting the machine when we're fuzzing, by execing the thing at contents of 0000, the trap vector. So we actually get 6 functions for the cost of 5. It's very, very easy to do. But it's still not going to be called at this point because we've not installed it yet. And installing it is simple as doing that. We basically write the address of that string, of not the string itself now, but of our patch into the trace patch mod vector, and we're done. So we're ready. Where do we go from here? Okay. Right. We want to recover the binary. We've got the patch in, we've got the stuff. I've done some userland code that basically just exposes those functions through. So we look at, this is a shell actually running on my phone. The utilities code BCMWLAN, I've just exposed alloc, read, write, free, and I've got extract. There's no exec in there. Exec's not in the help message. Exec's in there as well. If you run info is just a repackaging of read that looks up the DPPP, looks up the HNDRD debug, prints that out for you. And to get the ROM, we just say extract it to file. And this is where I have an admission to make. I told you a lie at the beginning. I said that you can't read the ROM. And that's because every single presentation I've seen says this, and everybody goes through this patching shenanigans, and you read the comments on Beniamini's articles at Project Zero, the NexMon people have waded in and said, this is how we do things. You can actually read it, because if you look at the block of memory down there, that's the RAM that we want to read, and it says, yes, here's, it's loading at 160000, it's 8800 bytes long, 80,000. But if you look earlier, there's another mapping up there. This one starts at address 20 and goes on for DFFE0 bytes. That's exactly 20 bytes short of the E, the big thing. So we've got the ROM, and we can read it out directly using mem control. We just punch that into the commands, we get it. Unfortunately, the format looks a bit like XXD, but you can't use it to revert and get the binary back. We're getting close. But a little bit of shell scriptry gets you that image back. Okay, I'll skip that. Right, so you've got your binary, you've now got the ROM, you've got the RAM, you can stick them together, you can start assembling them, you're going to spend an hour or two just resolving all the references, making sure everything patches up, going through and having all the usual fun. And now you can start to get to grips with it. It's great, that's exciting. Right. What's wrong, though, is you're going to see this happen, and not just once, like hundreds of times. This piece of code is Hopper. Hopper's got a really lovely UI. It's actually much better than Ghidra. It's certainly a lot better than IDA. Because anything in that kind of yellowy color is a procedure. It knows this is something that is actual function. It does something. And anything with a white background like that is just random, there's just instructions that aren't called by anything that it can work out. And that's because this function here, the very first thing it does is branch. And that's it, end of function. It's going somewhere else. But that's in ROM. Why would they have all this crap in there like that? That doesn't make any sense, especially because what follows does actually look quite reasonable. And as I say, I've did a little bit of scriptry as well. I've marked them all up here and tagged them. There are hundreds of undefined functions in the ROM that just calling out into the RAM. It makes no sense because the RAM, every time we repackage it, things could be in different locations. What actually is going on is it's making use of something called the flash patch and breakpoint unit in the R4 processor. It exists in actually most ARM Cortex CPUs. It's a way of changing the flow of data that CPU sees. You can set up a table, there's a debug registers control it, that say, when you try to load from this address, you try to do a literal load or an instruction load, I want you to read this many bytes from this location in RAM instead. That allows them to patch any function in ROM and hook it to do things in RAM. So they don't have to have a patch mod vector for everything, just for the things they knew they were going to overwrite. But anything that comes up as a must fix gets fixed like this. And there's a couple of hundred entries you can do on some of these CPUs that allow you to do that. The good thing from an exploring point of view is it means there's nothing you can't hook yourself as well. Because use the debug platform to upload a piece of code, and you can then say, I want this to be hook whatever function I want in memory. At any point I want something called, I can hook it. That's really, really, really powerful. The main problem is that many of these debug patches are already fixed, they're already in use, and you're going to find that you may even exceed the table size on the particular CPU you've got. But it's hugely, hugely useful. The other thing that's really good to look at is the device console, because you can now call printf inside your inside any patches you want to upload on top. And like I said, I've got my little debug platform. Its job is really to get other code into the CPU. And so if I want to find out if something's happened, the easiest way to do it is to print the error log, because otherwise I might not be able to interact with it if it's outside the normal flow of me poking it from the outside. And here we see an example where the console pointer points to a console object, it points to the buffer. Here you can see, just normal startup messages. And the final thing that I do once we've got this far is compile code for the WNIC. You don't need to write in assembler. Write in assembler. Even me, I like assembler. I've been writing in assembler since I was a kid. I think it's great. It's just very painful. So you can write in C instead, or C++ even. And you can upload that code, as long as you get the right compiler options. C++, you've got to turn off exceptions and all kinds of stuff. But if you've got the ARM NUN EABI toolchain installed on your machine, you can do it. These are the commands you do. Basically, compile it F-free stand-in, position independent code, compile it for the right processor. When you link it no standard lib. You're going to need a linker script to tell it what the entry point of the code is, where which function to put first, in effect. But that's like 2 or 3 lines of script. And then ARM NUN EABI obj copy. Obj copy just takes an ELF file, strips out the code that you care about, and dumps that into an image file. And you can then upload that using the debug platform. So that gets you to the point where you've now tamed the CPU, because you've got all the code down, you've analyzed the code, you can change the code, and you can change the flow of what's there, even when it's in ROM. So you've pretty much got full power over the CPU, over the embedded processor. It's not the CPU, that's the host device. That brings me to the next part, which is how do we go about breaking it? Have we got much longer?
You're over, but it's
Oh, well, sorry. We'll talk about fuzzing and exploiting. Exploiting I'm not really going to cover today properly. But in terms of fuzzing, I'm going to encourage you to look at perhaps some of the older, less sexy fuzzing technologies, because everybody likes AFL and libfuzzer, and they're great, but you kind of need source and you kind of need a tractable environment. You're talking about a binary here. Fuzzing in binaries is a really interesting and quite a cutting-edge area, to be honest, because you're kind of forced back to more old technologies. And I suppose the main first thing we should do is decide what we're going to fuzz. And since we're on an Apple platform, I'm going to talk about fuzzing some Apple-specific behaviors. But Beniamini, and I know I referred to the paper, the Project Zero article a couple of times already, went after an 802.11 facility called TDLS. And that's used to set up a tunnel data link between, say, your laptop and your Google Chromecast, without going via the access point, because normally every packet with access point, then do the dance back there, and that's just halving your bandwidth. If you can provide a tunnel between the two that's secure, then fine, and that's what TDLS does. Apple have a very similar thing in AWDL. Apple also have the Bonjour protocol. Bonjour is just a repackaging, it's MDNS under the skin. And these two protocols kind of work quite nicely together. AWDL, I'm going to recommend you read Stuter's paper. I've linked to it here. It's the only documentation on AWDL you're going to find. And it's basically a way of getting more than one channel out to Wi-Fi. It's saying, we will, for a certain period, because the card can only broadcast and receive on one frequency at once, or one channel at once, then what it does is it says, well, at certain points, I will switch to another frequency and I will listen there. And then I will go back. And so this logical channel, if you can synchronize everybody to do that all on a common clock, you can have the effect of having 2 channels. You shouldn't miss traffic on the first channel because you're off over here. You could potentially do stuff. But that would be the case anyway. It's a really kind of like a useful, and it's equivalent of what TDLS is. And it uses 3 special social channels to negotiate, to synchronize, get times. It also incorporates into the AWDL frame, which I'm going to point out, this isn't what an AWDL frame looks like. It incorporates into that frame, which you're seeing in Wireshark at the side. Wireshark has support, since version 3, which came out in February, has support for this. You can actually see the AWDL traffic, and you can actually sniff it and play around with it. It's quite useful. But one of the things you're going to see is that Bonjour traffic, MDNS, service discovery frames are piggybacked onto the end of the AWDL action frames. AWDL itself is not anything particularly new. The first part of it is a standard 802.11 management frame. The second part of it is AWDL itself. And the really nice thing about that is it's got tag length values at the end. And TLVs are lovely things to fuzz with. For fuzzing, I use BooFuzz. Probably the most important thing is to keep all your crash reports and to give them to Apple. You don't want to be crashing things and handing those off. So turn off your crash reports. That's quite straightforward to do. You take all those buttons, you turn them off, you get those buttons instead. Try not to annoy your neighbors. I'm lucky because I do the cell phone stuff. I've got a Faraday cage, so I can actually run this in a Faraday cage. But even in my house, you can see like 15 Wi-Fi LANs without trying. And that's like trebled from last year or something. It's getting ridiculous now. So yeah, you'll annoy your neighbors if you're fuzzing because that's just a continuous stream of traffic on one channel. In my particular setup, I actually go a bit further. I've got a setup that looks a bit like this. We've got a fuzzing box at the end, which is a little Alex 3D board. I've got a Wi-Fi router to which the fuzz target connects, just to lock it to one channel and keep it all in the same place. I use the social channels that AWDL defines. And then the AWDL fuzzer, the MDNS fuzzer, basically injects frames over the air, but it's got to somehow know what's going on in the back end. And that's why I said where the firmware stuff is different to doing it on a host. Because if you're doing things on a host, you've got a process monitor, like Bufuzz has got a ProcMon that it'll ship. And you can have a Windows or a Unix one, and it basically waits for a process to fall over, and it's about monitoring that way. Can't do that in firmware. You've got to be a lot cleverer. And so what I've done is I've ripped off the procmon.py, re-implemented it as a C program, and embedded that to run on the actual device. And then we use a tunnel, so a libproxy connection to connect to the device so that I can control it from remotely. I'm very conscious of my time, I apologize. Crash detection is difficult. That's basically the important thing is just this little C++ program. It sits on the host side, not on the WNIC. It literally just runs on the iOS platform, and it monitors the device to see if it's crashed yet. It does that because if the device ever resets, it'll basically wipe out my patch because it gets reinstalled. It happens very quickly. So I then reinstall it by running a memcontrol script from within my process monitor. With those things done, you should be good. Just set off and go fuzzing. It's probably the start of your problems because there are problems with silent memory corruptions. What you corrupt is not necessarily what actually caused the crash. The crash may happen sometime later, especially on an embedded device because we don't have the kind of memory protections you have in a Unix process where, you've written a bad address, bang, you're over. Or you want to write address 0, that's in RAM? Yeah, fine, no problems whatsoever. You want to trash over there? I'm quite happy to let you do that. So you do have a lot more problems in reproducing crashes. If a crash is reproducible, that's a really good candidate. If it's not reproducible, don't waste your time, move on, because it's just hard at this point. And so I've put a link down to a really good paper from last year's NDSS called What You Corrupt is Not What You Crash. That really gives a flavor of what's going on. I'll rush in through to my end because my exploit dev part is really one slide, and I'm not even talking about exploit dev. Because at this point, you've tamed the WNIC, you've installed, you've reverse engineered it, you've got code running on, you're capable of hooking anything you want. You've got candidate crashes, and then you can go your normal exploit process, because this is like hacking a 1990s computer. There's no ASLR, there's no DEP, there's none of those things in there. There's no canaries in there. It is really a case of you find a buffer overflow, you've got execute access. That part's actually quite nice. From there, you can turn around and pivot and start thinking, well, I could fuzz the host, because I've had that ever since the first part of the access. Once I've got code running on the WNIC, I can use it and turn around to fuzz the host from there, because they just don't expect it to happen that way. It causes a lot of crashes. It causes an awful lot of reboots on your iOS machine, but it is a really good way of finding just how flaky that stuff is. Because most device driver software does not expect to be talking to a hostile device. It's that simple. My last slide is basically to wrap up with where I started off. I started with the real-world impacts of iOS malware. And basically, there's this huge market that's sprung up. You can go to Zerodium. If you've got a full chain exploit the way that Beniamini did, it's allegedly worth 6-figure sums and stuff like that. There's a reason for that. The people who are buying this stuff are not nice people. They're doing rather nasty things. I hope I put that in perspective. There's definitely bad things going on. There are good things as well. It's been used, this kind of malware has been used to intercept people traffickers. It's been used to intercept smugglers and poachers. And that's good. I think we probably all support those kind of things. But it's also been used to attack the civil rights of people. It's been used to undermine journalists and people like that. So what I'm going to ask you, and if you remember nothing else about this talk, and then went on way too long, is that I'd like to ask you, if you ever get involved in stuff like this, don't sell your exploits to creeps. It's that simple. By all means sell them, by all means find a market. Don't sell them to creeps. Thank you.